This video is about how math, especially game theory, has completely revolutionized biology since the 20th century. We will learn the very basics of game theory and theory of evolution, and explore how the evolutions of certain behaviors in the nature can be simulated based on mathematical principles by integrating the two. In the end, we will build a famous model, hooked off game with Retaliator from complete scratch. This video will initially use everyday language for better understanding, and gradually incorporate mathematics. Although it is quite a long video, if you watch it till the end, your perspective on the world might change. Even if you don't have any background knowledge about population genetics and evolutionary biology, you shouldn't have much difficulty understanding with high school math and biology. I welcome any criticism or corrections as they contribute to enriching the project. Let's begin with game theory first. So, what is a game theory? Is it a theory about video games? In actuality, game theory is the study of mathematical models of strategic interactions among rational agents. In game theory, these interactions are seen through the lens of mathematics. Before delving deep into the subject, let's take a brief look at the history of game theory. Famous precursors such as Girolamo Cardano, Blaise Pascal, Christian Huygens, James Waldegrave, and Antoine Augustin Cournot have made notable contributions in this field, mostly due to gambling. Anyway, modern game theory didn't become an independent field until John von Neumann's paper on the theory of games of strategy in 1928. He further developed the field by co-authoring Theory of Games and Economic Behavior with Oskar Morgenstern in 1944. Furthermore, the RAND Corporation conducted investigations into game theory with the aim of applying it to global nuclear strategy. Meanwhile, John Nash developed a criterion for the mutual consistency of player strategies known as Nash equilibrium. Game theory has had a profound influence on various disciplines, including politics, economics, philosophy, social science, biology, and many others. It opened up a whole new chapter, particularly in the field of biology. Before we delve into the concept of game theory, let's define some terms. A game refers to a formal representation of a situation or interaction where multiple players make decisions that affect the outcomes. A game consists of a set of players, a set of strategies available to each player, and a set of payoffs associated with the possible outcomes. A player is an individual or entity that participates in the game. Each player is assumed to have their own preferences, goals, and decision-making capabilities. Even whether or a robot can be a player. A strategy represents a specific plan of action or choice that a player can take in the game. It determines how a player will behave or make decisions in different situations within the game. Payoff refers to the outcome or reward that a player receives based on the joint actions and strategies of all players in the game. There are various ways to categorize games, but we will focus on 4 categories for now. Normal form games are designed to analyze situations involving simultaneous decision-making. They employ a matrix representation known as a payoff matrix. Extensive form games, on the other hand, capture decision-making processes that unfold sequentially over time. They employ a game tree representation. Cooperative games involve players who can form alliances, negotiate, and collaborate to achieve outcomes that benefit the group as a whole. In these games, players can communicate, make binding agreements, and enforce cooperative strategies. Non-cooperative games focus on strategic interactions where players act independently and make decisions without making binding agreements. Symmetric games are characterized by identical or symmetrical payoffs and strategies for all players involved. In these games, each player faces the same set of strategic choices, and the resulting payoffs are the same regardless of the player's identity. Asymmetric games, in contrast, are characterized by differences in payoffs and strategies among the players. Each player may have distinct roles, capabilities, or information, leading to varying strategic options and potential outcomes. Zero-sum games are characterized by a fixed sum of payoffs, where the gain of one player is directly offset by the loss of another player. Non-zero-sum games are characterized by the potential for outcomes where the total utility can increase or decrease. Now let's talk about the prisoner's dilemma, a famous scenario explained by William Poundstone in his 1993 book, Prisoner's Dilemma. Imagine 2 members of a criminal gang who get caught and end up in separate cells, unable to talk to each other. The police don't have enough evidence to convict them of the main charge, so they decide to give each prisoner a 2-year sentence on a lesser charge. Here's the twist: the police offer both prisoners a tempting deal. Scenario 1. If A and B each betrays the other, they each serve 5 years in prison. Scenario 2. If A betrays B but B remains silent, A will be set free while B serves 10 years in prison. Scenario 3. If A remains silent but B betrays A will serve 10 years in prison and B will be set free. Scenario 4. If A and B both remain silent, they will each serve the lesser charge of 2 years in prison. A domino strategy is a strategy that yields the highest payoff for a player, regardless of the strategies chosen by other players. It is a strategy that is optimal for a player regardless of the circumstances or actions of their opponents. A dominated strategy, in contrast, is a strategy that results in a lower payoff for a player compared to at least one other available strategy, regardless of the strategies chosen by other players. In the prisoner's dilemma, betraying the other player is indeed the dominant strategy for both players, as it offers the highest payoff regardless of the opponent's choice. The dilemma also highlights that decisions made under collective rationality may differ from those made under individual rationality. In this game, loyalty to one's partner is considered irrational. Iterated elimination of strictly dominated strategies is a process where players systematically eliminate strategies that are always inferior, regardless of the choices made by other players. When all strictly dominated strategies are excluded and only one strategy pair remains, the strategy pair betrayal is called dominant strategy equilibrium. The stag hunt by Rousseau is a famous story that appeared in the book Discourse on Inequality. In Rousseau's story, two hunters are faced with the decision to independently choose between hunting a stag or a hare, without assurance of the other's choice. The hunters are aware that the sole means of successfully hunting a stag is by doing it together all at once. While one hunter can easily capture a hare alone with less effort and time, the hare guarantees less value compared to a stag. However, it would be tempting enough to independently pursue a hare. The payoff matrix is as follows. If games in reality always had dominant strategy equilibrium, analysis would be a piece of cake. It would be just too obvious. However, in actuality, real-life games are hardly this simple. This particular game doesn't have a dominant strategy equilibrium. You can pause and check it for yourself. So, what do we do now? We will need to find another equilibrium. If Hunter A chooses to go for a stag, Hunter B has two choices, a hare or a stag. If Hunter B goes for a stag, he would receive a reward of 2. If Hunter B goes for a hare, he would receive a reward of 1. In this situation, Hunter B is likely to choose a stag, as it is his best response. We've just learned about the best response. In game theory, the best response refers to the strategy or strategies that yields the most favorable outcome for a player, considering other players' strategies as given. The same principle applies to Hunter A. Therefore, the stag-stag pair is where both players select their best response to each other. We've just learned Nash equilibrium. The concept of a best response is central to John Nash's most well-known contribution, the Nash equilibrium, which is the point at which each player in a game has chosen the best response or one of the best responses to the strategies of other players. In Rousseau's game, the hunters don't trust each other. This holds true in reality to a certain extent. However, we can at least predict the opponent's behavior if we know the rules. In a Nash equilibrium, each player is assumed to know the equilibrium strategies of the other players, and no one has anything to gain by changing their own strategies so that the equilibrium can be maintained once it is reached. Nash equilibrium doesn't always exist. Take the game of rock, paper, scissors for example. When my opponent plays scissors, the optimal response for me would be to play rock. However, the optimal response for my opponent to my rock is to play paper. In this way, there is no Nash equilibrium in the rock, paper, scissors game. Also, it is important to note that a game can have more than one Nash equilibrium. Let's consider a scenario where Hunter A chooses to go for a hare, and Hunter B has two choices, a hare or a stag. If Hunter B decides to go for a hare, both hunters will receive a modest reward of 1. However, if Hunter B chooses to go for a stag, he will receive no reward. Hence, this game exhibits two distinct Nash equilibria. Nash equilibrium does have its limitations. When multiple Nash equilibria are present in a game, it doesn't provide a clear indication of which equilibrium will be realized in practice. It simply tells us that the players have no incentive to deviate from their current strategies. Despite these limitations, Nash equilibrium remains a valuable tool for analyzing non-cooperative games. So far, we focused on players using one strategy, which is known as a pure strategy. Now we are going to delve into mixed strategies. If a pitcher can choose between a fastball or a breaking ball, pure strategies would mean using fastballs all the time or breaking balls all the time. Mixed strategy, on the other hand, would involve mixing them at a certain ratio. For example, throwing 4 fastballs and 6 breaking balls out of 10 pitches. When a pitcher has a 100% chance of throwing a fastball and a 0% chance of a breaking ball, it is considered as a pure strategy. From now on, we will rewrite the previous concepts using mixed strategies. We will be using some math symbols from now on. A mixed strategy consists of a set of possible moves and probability distribution, which indicates the frequency or weight assigned to each move to be played. Sigma sub A1 means the probability that A chooses strategy 1. One's mixed strategy can be written like this. The pi symbol generally represents a payoff function. Pi sub A of stack outputs player A's payoff when both choose to unstack. U denotes the expected payoff of a player. U sub A of sigma sub A and sigma sub B informs us about player A's payoff when A utilizes mixed strategy sigma sub A and B employs sigma sub B. The player's payoff for a mixed strategy is a weighted average of the payoffs from its pure strategies. When Hunter A chooses to hunt a stag and Hunter B also chooses to hunt a stag, we multiply the payoff Hunter A by the probability that each player chooses to hunt a stag. Hunter A chooses a stag with a 70% probability and a hare with a 30% probability. Hunter B selects a stag with a 30% probability and a hare with a 70% probability. By handling all possible cases in this way, we can get U sub A of sigma sub A and sigma sub B. There were 2 Nash equilibria in the stag hunt game. However, we derived them solely from pure strategies. From now on, when we refer to H sub 1, we will be referring to a mixed strategy that uses strategy 1 with a 100% probability. Here, it would correspond to hunting a stag. The payoff for Hunter A when he only hunts stag can be calculated using the same formula as before. Since Hunter A has a probability of 0 of hunting hares, only the first term remains. The payoff obtained when Hunter A only hunts hare is easily calculated as follows. Additionally, since this game has only 2 strategies, the mixed strategy of Hunter B can be expressed as follows. Then Hunter A's expected rewards for only hunting stags and only hunting hares are as follows. A's move will depend on B's move. If the payoff obtained when Hunter A only hunts stag is greater than the payoff obtained when Hunter A only hunts hares, it is natural for Hunter A to choose to hunt stag. That means if sigma sub B stag is larger than 1/2, A will always hunt stags. When we flip the inequality sign, A will go for a hare all the time. What would you say if they are equal? Should Hunter A use a 50-50 or 70-30 ratio? The answer is, it doesn't matter. Any ratio of a mixed strategy would be fine when sigma sub B stag is exactly 0.5. If we draw a graph for the best response of player A, it will look like this. Since the game is symmetrical and we can transpose the payoff matrix, we can easily draw the best response of player B. The graphs intersect at 3 points, and 2 of them seem familiar. Right. They are the pure strategy Nash equilibria. This intersection is a new one. It is another Nash equilibrium. It is a mixed strategy Nash equilibrium in this game, represented by the strategy pair sigma sub A, sigma sub B. Now let's move on to theory of evolution. Generally, when we hear the term evolution, we imagine something being improved or enhanced, and we understand degeneration as the opposite. However, in biology that is not the case. Even the regression of eyesight is considered as evolution for cave and deep-sea dwelling animals. Among this diverse range of genes, those that are more suited to the environment are naturally selected, leading to changes in the overall characteristics of the biological population. The fundamental principles of evolution are as follows. Genes continuously diversify, and their changes can accumulate through genetics. Under natural selection, various organisms survive to different extents. We might still wonder how a complex system such as an eye can emerge from nothing. The chance still seems so slim. The iconic infinite monkey theorem by French mathematician Emile Borel states that a monkey hitting keys at random on a typewriter for an infinite amount of time will almost surely type any given text, such as the complete works of William Shakespeare. Thinking about the probability of typing the sentence to be or not to be on a typewriter with 27 keys. The sentence to be or not to be has 18 letters including spaces. Suppose that the keys are pressed randomly and independently, meaning that each key has an equal chance of being pressed, regardless of what key was pressed previously. The chance that the first letter is T is 1/27th, and the chance that the second letter is O is also 1/27th, and so on. Therefore, the probability of the consecutive 18-letter spelling to be or not to be is 1/27th to the power of 18. If it takes 10 seconds for each attempt, it would take an enormous amount of time. Maybe monkeys would get angry. You want to write Hamlet with monkeys? Soon every typewriter will be smashed or covered with monkey poop. We need another solution. What if I told you if we can apply evolution to them? Now this monkey-made gibberish reproduces, and mutation takes place. Out of unmatched letters to the target sentence, one letter changes every generation at random. After a few hundred generations, we get to be or not to be. It might seem big, but compared to 1/27th to the power of 18, it is a bang for the buck. This simulation doesn't accurately describe real mutation and natural selection, but you get the rough idea. If we were to employ monkeys to obtain something in one attempt, it would take forever. However, if selection accumulates over generations, it can happen in a much shorter time. If evolution relies solely on the one-step selection of expecting something to happen all at once, it would have been impossible. There might be a misunderstanding in the typewriter analogy. We consciously compare the results with to be or not to be. But it is important to note that nature doesn't possess a conscious mind or an ultimate goal, like a blind watchmaker. In retrospect, it may appear as if the evolutionary process has been intentionally leading towards the current form, resembling the actions of an intellectual being. However, it is important to recognize that throughout generations, incremental changes have been naturally selected bit by bit, resulting in the accumulation of these changes over time. Now we are going to put the two together. Evolutionary game theory is a branch of game theory that applies principles of evolutionary biology to study strategic interaction among individuals in a population. It aims to understand how social behaviors and strategies evolve over time through the process of natural selection. In traditional game theory, players make decisions based on their rationality. However, in evolutionary game theory, individuals are seen as biological entities with inheritable traits. We will assume many players with various strategy are in the pool. They just perform strategies programmed in their genes and interact with one another and reproduce based on their fitness. Reproduction is a reward for them. Let's return to the stag hunt game and transform our previous game theoretical approach into an evolutionary perspective. Let's denote the proportion of individuals using the stag strategy within the population as P. Let's consider the red dots as the payoff for the stag strategy and the blue dots as the payoff for the hare strategy. When P is 1, the payoff for the stag strategy is 2, while the payoff for the hare strategy is 1. When P is 0, the hare strategy easily yields a payoff of 1, while the stag strategy always results in a payoff of 0. This game doesn't seem to have any non-linearity in it. So let's connect the 2 points. The red line represents the payoff for the stag strategy, and the blue line represents the payoff for the hare strategy. Let's perform a quick check. What if P is 0.3? It means that player A randomly interact with other players, encountering stag strategy users with a 30% chance and hare strategy users with a 70% chance. If player A uses the stag strategy, the expected payoff will be 0.6, which is the height of the graph at P equals 0.3. We can also obtain 0.6 by the mixed strategy payoff. So, what can we do with these graphs? We can analyze evolutionary stability. Evolutionarily stable strategy refers to a strategy in a population that, if adopted by a certain proportion of individuals, cannot be invaded by any alternative strategy. Even if mutations or newcomers appear, they will eventually disappear if they receive lower payoffs and cannot reproduce well. If 1% of the population suddenly changes to the hare strategy in a world filled with stag strategy users, P becomes 0.99. The payoff for the stag strategy, which is the height of the dark red dot, is still higher than the dark blue dot, and the hare strategy goes extinct after a few generations. If 1% of the population changes to the stag strategy in a world filled with hare strategy users, P becomes 0.01. In this case, hare strategy guarantees higher payoff, so the stag strategy cannot survive through generations. It's simple. If everyone around you is hunting only stag, it's also profitable to hunt stag, and it would be foolish to hunt stag alone if everyone around you is hunting only hares. Therefore, they are evolutionarily stable strategy. Both hare and stag strategies are resistant to the alternative strategy. On the other hand, evolutionarily stable state refers to a stable state or condition that a population reaches during the course of evolution. It represents a stable state of strategies within a population. It shares similarities with mixed strategy Nash equilibrium. Among individuals, if half of them hunt hares and the other half hunt stag, P equals 0.5, the half hunting hares will still receive a pay of 1. When randomly interacting with the others, the individuals using the stag strategy will receive a payoff of 2 in half of the cases and a payoff of 0 in the other half. resulting in an average payoff of 1. In evolutionary game theory, payoffs are considered as fitness, which determines the reproductive success of the next generation. Therefore, if an equal number of offspring is produced, the state of p equals 0.5 remains unchanged and becomes an equilibrium. The most important one in this video, Hawk-Dove game, is as follows. Suppose there is a group of birds, and each individual competes for valuable resources such as or shelter, using either hawk or dove strategy. When two hawks meet, they fight and one wins while the other loses. The winner takes all the resources and the loser incurs a cost such as energy consumption and wounds. For now, we assume that when two hawks meet, outcome is randomly determined. When a hawk meets a dove, the hawk wins and takes all the resources, while the dove simply retreats without any cost. If two doves meet, they peacefully split the resources in half. Since individuals interact randomly and sufficiently often, we can express the expected values as shown in the following table. V denotes valuable resources, and C denotes cost of a hawk. We will assume V equals 2 and C equals 3 throughout the whole video. The following results are obtained. Let P be the proportion of hawks. The payoff of the dove is high when P equals 1 because all the hawks are fighting and hurting each other. So when the dove strategy invades by not engaging in fights, the hawk strategy is invaded. On the other hand, when the proportion of doves is high, the hawk easily invades because it exploits the doves. In the hawk-dove game, both strategies are not evolutionarily stable. Then we can imagine that we can find balance somewhere in between. If their payoffs are equal, the ratio between the two will not change. At P equals 2/3 or V over C, we can see that both players have the same payoff. At this point, even if the existing state is perturbed, it is restored. Hawk-Dove game doesn't have an evolutionarily stable strategy, but has an evolutionarily stable state. Now we need to know the dynamics to see not only part around equilibria, but also the whole picture. We will learn replicator dynamics. Before that, let's verify whether what we're doing is even valid. These models involve simulating the evolution of behaviors over many generations. These models may appear overly simplistic and therefore unrealistic. Can we rule out all the complexity of reality like Alexander the Great cutting the Gordian knot? Despite these concerns, mathematical modeling is highly useful. The behavior of human beings with emotion is analyzed through a mathematical approach called game theory. Although the evolution and reproduction of living organisms may seem unrelated to mathematics, we can gain a lot of insights by looking at the changes of replicators and populations of living organisms through a mathematical lens. One may wonder what significance there is in creating a model that excludes many aspects of reality. Mathematical models sacrifice details and gain traceability and clarity. Clarity can be understood as follows. We look at various maps. There are maps that include topographical satellite images, maps that only show subway routes, and maps of recommended restaurants. These maps limit information according to their purposes and deliver it to us in a clearer manner. If a map combines satellite images, subway routes, and restaurants all at once, it may be closer to reality, but it won't be a map that can be understood at a glance. Therefore, the game theoretical approach focuses only on the few characteristics we are interested in and temporarily sets aside the rest. Traceability refers to the ability to track and understand changes in the system. Since mathematical models are mathematically defined, we can trace and understand every moment of change, just as we trace the entire production process to find problems when a product malfunctions. At this point, you might think, okay, let's make a simple model and just simulate everything. With the rapid advancement of computer technology, it is indeed easier than ever to simulate. However, simulations have their limitations. Simulations often involve multiple parameters. You would input parameters such as initial population size, mortality rate when infected with a disease, and probability of interaction between individuals. If you set the initial population size in the simulations to 100, 200, 300, the mortality rate to 0.1, 0.2, 0.3, and the interaction probability to 0.5, 0.7, 0.9, then you have to run simulation 27 times. Since even slight changes in these parameters can lead to unpredictable results, you will want to cover a wider range with smaller intervals for all the cases. The computational load will skyrocket soon. Reproducibility is essential for a theory to be accepted. If apples fall downwards when I conduct an experiment, but fly to the right or float in the air, or fly to the camera when someone else conducts the same experiment, it will not be accepted. This is called reproducibility. In simulations, when randomness or probability is involved, the same result may not be produced each time. Back to replicator dynamics, let's explore the concept called viability selection. The first thing to do is to mathematically represent the events that can change the distribution of genotypes within the population during one generation. We're not going to split hairs about technical genetic stuff like diploid, sexual reproduction, zygotes, and chromosomes and such. Just assume they make a baby clone for now. Let's assume one can have either gene A or gene B, and each gene directly affects what an entity does. This is a simple selection model based on survival rates. At a given generation T, babies grow and their survival or death depends on whether their characteristics are compatible with the surrounding environment. If they survive, they develop into adults. Adults produce new babies to live in the next generation T plus 1, and they die. The babies at T plus 1 go through the same process again. Generations are discrete, meaning that all individuals grow, reproduce, and die at the same time, not overlapping across generations at all. There are n individuals in the population. We will consider n to be large enough to ignore sampling error. We want to know the proportion of a specific gene within the population across generations, which naturally ranges from 0 to 1. Mathematicians studying social science or dynamic systems refer to this frequency as a state variable. The number of state variables is usually one less than number of genes. If individuals in the population can have either A or B, when the proportion of A is P, the proportion of B is 1 minus P. If there are 3 traits, the proportions of A, B, and C would be P, Q, and 1 minus P minus Q. To understand the changes occurring over numerous generations, we will conduct a census every generation. In the model with only 2 traits A and B, the value of P representing the proportion of trait A at a given time T can be defined as follows. N represents the current total number of individuals. By rearranging the equation, we find that the number of babies with gene A in the population is N times P, and the number of babies with gene B is N times 1 minus P. Now the babies will grow, and some will survive. V of A and V of B represent the probabilities of survival until adulthood for babies with trait A and B. For example, if VA is 0.5, half of the babies with trait A will develop into adults and reproduce. Now the proportion of A adults in the population at the end of this generation, P prime, can be calculated. We can calculate the next generation's babies, P double prime, which is pretty much interchangeable with P prime. In this model, regardless of their traits, all adults engage in asexual reproduction individually and produce Z babies. Therefore, Z of A outputs the number of babies an A adult makes. Since we employ one entity, one baby policy, everyone produces the same number of babies and it doesn't affect ratio between A and B. Plus, V of A can be W of A, which means fitness of entities with A trait, defined as V of A times Z of A. Now we can erase the N's and Z's. Now we can determine how P changes at each generation. Let's denote P in the first generation as P sub 1, then P sub 2 can be calculated as follows. Similarly, we can obtain P sub 3 by replacing P sub 1 with P sub 2. This is called recursion. We can elegantly express this using a difference equation. In general, the denominator part P times W of A plus 1 minus P times W of B is represented as W bar, which denotes the average fitness within the population. Finally, the equation can be expressed as follows. This difference equation called the replicator dynamics of selection based on fitness. Since we will use it very frequently in the future, it is important to understand it accurately before moving on. The variance of traits within the population is P times 1 minus P because it follows Bernoulli distribution. When one trait becomes prevalent, the variance decreases. The variance is maximized when there is an equal distribution of the 2 traits, P equals 0.5. Delta P is at its maximum when P times 1 minus P is at its maximum. Therefore, selection pressure is the strongest at P equals 0.5. When the variance reaches 0, that is, when P times 1 minus P equals 0, delta P becomes 0, and the state remains unchanged. The condition P times 1 minus P equals 0 implies that P is either 0 or 1, indicating a population composed of only one trait. The second part simply represents the ratio of increase or decrease of trait A compared to trait B. If trait A is better adapted than trait B, this will be greater than 0. And as generation passes and there is variation in genes, P will increase. Conversely, if this is less than 0, P will decrease with each generation. There are three main methods that can be used to analyze dynamics of games. An explicit solution is an expression that gives us the frequency of each type at any time. This method is not always applicable and can only be used when the model is extremely simple. Now let's find out the number of individuals with trait A in the generation t plus 1. It is the number of individuals with trait A, not the frequency. V of A and V of B are simply constants, and in the simple model we are dealing with, they do not vary with P. Let's consider t plus 2, now look at t plus 3. Now let's generalize this to easily determine the number of individuals with trait A at any given time t. Similarly, we can easily determine the number of individuals with trait B using the same logic. Now we can express the ratio of trait A in any generation as follows. We obtain the desired function. Assuming A has a fitness of 0.8, B has a fitness of 0.5, and the initial population consists of 1 individual with gene A and 99 individuals with gene B, let's plot the graph. In this model, since A has a higher fitness, initially it represents only 1% of the population, but its proportion increases within the population over time, eventually resulting in all individuals being A. The rate of change is initially very slow, but gradually increases. It reaches its maximum when the variance is at its maximum. The second method is equilibrium analysis. Equilibrium analysis is a widely used method. This method involves finding the point where there is no change, which means delta P equals 0. Now let's find the point where delta P becomes 0. The easiest way for delta P to become 0 in this equation is when the P times 1 minus P becomes 0. It is also possible when V of A minus V of B equals 0. Intuitively, if the population consists of only one type, there will be no change. In that case, P equals 0 or 1. And if the two traits have the same fitness, they will reproduce in equal numbers and there will be no change in the ratio. The yellow graph represents our model. The dashed line represents the graph of P prime equals P. What does P prime equals P mean? It means that even if we input P, the next generation's value of P remains the same. It leads to delta P equals 0. Therefore, an equilibrium. The two intersections are equilibria. Let's determine whether it is stable or unstable in this situation. Let's assume that the red dot slightly deviates from equilibrium for some reason. What will happen next? Going through generations means plugging in the P into the difference equation to obtain the change and using delta P to obtain the next generation's value, repeating the process. This means the point on our model's graph moves horizontally to touch the dashed line, updating the value of P. Now P prime becomes P for the next generation, and it moves vertically to touch the model's graph to show us new generation's P prime. The vertical line's length is the delta P of each generation. Eventually, it reaches a state where P equals 1. Moving further away from the original equilibrium, if P is 1, is it a stable equilibrium? Let's slightly deviate from P equals 1. In the end, P will return to 1. Therefore, it is a stable equilibrium. The last is linear stability analysis. This method determines whether it is stable or not based on the slope at the equilibrium. If the slope at the equilibrium is between minus 1 and 1, we can consider it stable. Let's see why. First of all, the graph of P prime equals P has a slope of 1 at any point. So when the slope is 1, even if it deviates, it remains unchanged in the new position. However, if the slope of the graph is between minus 1 and 1, it means on the left side the graph passes over P prime equals P, and on the right side it passes under P prime equals P. Negative perturbation of P will lead to increasing P prime. Positive perturbation of P will lead to decreasing P prime. It means as generations repeat, it fluctuates less and less and eventually returns to the equilibrium. Now let's observe how HD game pans out over time. We can define such changes using a vector field. When a specific position is input, it tells us the direction and magnitude of force at the position like an electric field. Think of the initial conditions as points in a coordinate system. By placing an initial condition which represents the position of a point in a vector field, it tells us to which point it should move. By repeating this process, we can see the trajectory of the point. If the sum of applied forces on a point is 0, it'll be in equilibrium, not moving in any direction. You can see our points for HD game, and they are on a specific line. When there are two strategies, we will need a two-dimensional space to represent them. However, we remember that the state variables are always one less than the number of strategies, represented as p and 1 minus p. Therefore, instead of using the entire two-dimensional space, we can represent it using a one-dimensional line. Even with three strategy, we can represent them in a two-dimensional triangle formed by three one-dimensional lines. The same goes for four strategy system and so on. When there are k pure strategies, the k minus one-dimensional form is called a simplex. If we plot the three strategy system on xyz axis, the following triangle is formed and called a ternary plot. The points on this triangle satisfy the equation x plus y plus z plus equals 1. If there is a population consisting of strategy x only, it will correspond to 1, 0, 0. If all strategies are equally represented, it will correspond to 1 over 3, 1 over 3, 1 over 3. We can interpret a ternary plot using Viviani's theorem, which proves in an equilateral triangle, the sum of the distances from any interior point to the three sides of the triangle is equal to the altitude of the triangle. The closer a point representing the current state is to a specific vertex of the triangle, the larger the value of the strategy along that axis becomes. It indicates that the corresponding strategy is more prevalent. The line we are currently observing represents the internal state of a population where hawk and dove exist. Again, this is a simplex. The length of the red line is square root of 2. However, one end represents p equals 0 and the other represents p equals 1. So we are going to scale it accordingly for our convenience. The payoff matrix is as follows. The payoffs are of the player A for the sake of simplicity. Read V of H given D as the viability of a hawk, given that it interacts with a dove. Remember, we have been analyzing the game as if the interaction we are focusing on was the only factor for survival. But in actuality, there are countless factors. Normally, we can say that the influence we are analyzing isn't significant. The part other than this game that contributes is called baseline fitness. If the baseline fitness is too small, the fitness W of A can be negative. This doesn't make any sense. W of A equals V of A times Z of A. Both V of A and Z of A should be positive. We can't have minus 2 babies or survive with a minus 10% chance. Therefore, so should W of A. Additionally, it can lead us to random chaotic results. It is as if we set the time difference too big and the model doesn't properly capture subtle dynamics and lumps everything together at once. Therefore, we will set the baseline fitness large enough. Now we can calculate the expected payoff of a hawk and a dove. If the absolute value of delta p is large, the point on the simplex will move quickly in each generation. The formula for delta p is as follows. Now we can plot the one-dimensional vector field. It is too thin to see what's going on. Let's stretch it vertically a little bit. If there are many hawks within the population, they will engage in frequent fights, and this creates an opportunity for the dove to infiltrate. On the other hand, if there are many doves, hawks can easily exploit the doves. When W of H and WD are equal at PV over 3, resulting in delta P becoming 0, it is an equilibrium. We can see not only how it works near equilibria, but also how the whole system moves. Let's draw another axis representing delta P for better understanding. Now we will analyze three strategy systems, including the retaliator strategy. The retaliator behaves like a dove when encountering another dove, and it acts like a hawk when paired with a hawk. The payoff matrix including the retaliator strategy is as follows. If we define the proportion of retaliators as Q, then the fitness of each strategy is as follows. We will use the ternary plot that we just learned. Now let's spread multiple points on the simplex and see where they flow. Let's imagine a place filled with doves. We already know that rare hawks can invade a population of doves and vice versa. In this case, if a retaliator enters, it behaves the same as doves, resulting in no difference in payoff. It won't disappear and will stay still. If a dove infiltrates a world filled with retaliators, since everyone behaves the same, the dove doesn't disappear. In the world full of fights, few retaliators encounter each other, and they have a slight advantage over the hawks by not fighting. As a result, it may be slow at first, but later they rapidly drive the hawks to extinction. If there are only hawks and retaliators, the retaliators always have the advantage. Hawks cannot infiltrate a retaliator's world, but doves can. What about the case of a mixture of doves and retaliators? In a population of doves and retaliators, both obtain the same reward and coexist. Now, few hawks enter the population. When Q is smaller than the threshold, retaliators receive lower rewards compared to hawks that exploit doves or doves that avoid fights. As a result, retaliators go extinct, and a balance is achieved between hawks and doves. If Q is larger than the threshold, hawks go extinct because they encounter retaliators that rebel frequently enough, unlike doves just running away. Retaliator can invade the mixed HD equilibrium, where it receives higher payoff than hawks or doves. This is true when V is larger than C. Therefore, retaliators cannot invade hawk-dove equilibrium in our environment. In a world of hawks, both doves and retaliators can infiltrate individually. However, depending on whether they infiltrate simultaneously or sequentially, the outcome differs. If they infiltrate simultaneously, doves have the advantage over retaliators who frequently engage in fights with hawks. This leads to a balance between hawks and doves, and retaliators go extinct. If retaliators appear first and shortly after doves appear, again, the system reaches the hawk-dove equilibrium. However, if some time passes while retaliators increase in number, and then doves are added, it results in a coexistence of doves and retaliators. The game can unfold in various directions depending on whether the strategies infiltrate individually or when they appear. Furthermore, if the values of V and C change, the game will undergo a complete transformation. Just like climate and environment change, V and C might not be the same across all generations of the game. Although it is a 3-strategy system, there is much to analyze. Additionally, the 4-strategy game can also be represented in a tetrahedron. Covering all of them will be too long, so I will conclude here. We predicted the competition among animals, which doesn't involve rationality or any knowledge of mathematics. Ironically, this is how math revolutionized biology. Thank you for watching this long video till the end. I hope this was a pleasant and intellectually stimulating experience. I will make a separate epilogue video including Q&A, production process, future plan and such. Your comments, subscriptions, likes, and donations greatly support future projects and much appreciated. Please leave a comment if you have any questions.